Science has contributed greatly to our lives. Through the application of science, we are able to develop new technology, or even invent a new medicine to treat different diseases. Chemistry is one of the most important areas in science. However, in order to understand chemistry, we must first learn about atomic structure. The Bohr's model is simple and very easy to understand. It is one of the most common models used worldwide nowadays. Through looking at Bohr's model, we are acknowledged of the number of energy levels and the number of electron an atom has. This is Bohr's atomic model of aluminium. Aluminium has 13 electrons, and the electrons are arranged in a 2-8-3 pattern. Although this model is commonly used, it has limitations. Its limitations can be seen when we look at the successive ionization energy of an atom. Let's use aluminium as an example. According to Bohr's model, the 4th and 11th ionization energy should increase linearly, since all of these electrons are in the same energy level. However, the truth is that there is a jump between the 9th and the 10th ionization level. This proves that Bohr's model is not totally correct. Scientists then suggest that the second energy level is divided into two sublevels. The 4th and the 9th electron are removed from the 2p sublevel, while the 10th and the 11th electrons are removed from the 2s sublevel. Therefore, one of the limitations of Bohr's model is that it does not show the sublevel in an atom. Different letters are used to identify different sublevels. In the first energy level, there is one sublevel. We call this sublevel 1s. It can hold maximum 2 electrons in the sublevel. In the second energy level, there are two sublevels, 2s and 2p. 2s sublevels can hold 2 electrons, while 2p sublevel can hold 6 electrons. Therefore, the maximum number of electrons in the energy level is 8. Moving on to the third energy level, it contains the 3s, 3p, and 3d sublevels. The maximum number of electrons in each sublevel is 2, 6, and 10 respectively. Therefore, the energy level holds 18 electrons in maximum. In the fourth energy level, it can hold 32 electrons. To summarize, there are 4 sublevels, named S, P, D, and F. S orbital holds 2 electrons, P orbital holds 6 electrons, D orbital holds 10 electrons. The F orbital can hold 14 electrons. Another limitation of Bohr's model can be explained using the uncertainty principle. Werner Heisenberg came up with the uncertainty principle, explaining that it is impossible to give an exact measurement of where an electron is. Yet, in Bohr's model, Bohr assumes that the electron's positions can be described precisely. Heisenberg suggests that any attempt to measure the electron's positions will affect its motion. We can only give a probability picture of where electrons are likely to be found. Due to the uncertainty principle, the atomic wave model is created. The wave model does not describe the electron's positions precisely. Instead, it describes the electron-occupied orbitals, which is a region where there is a large chance in finding electrons.
As atomic orbitals shape seems like the Earth, is in sphere shape, and the p atomic orbital is formed with 3 dumbbell shapes. One of the dumbbell shapes is laid on the x-axis, which named as px orbital. The other is laid on the y-axis, which named as py orbital. And the last one is laid on the z-axis, which named as pz orbital. And here is the d atomic orbitals. In the d atomic orbitals, it is divided into 5 groups, which shows in the picture. And here is the high quality of how d atomic orbital look like. In s atomic orbitals, there are 1 pair of electrons in it, and in p orbitals, there are 6 electrons. In d orbitals, there are 10 electrons, and in f orbitals, there are 14 electrons. Therefore, in the 4th principal energy level, the maximum number of electrons is 32. And here is the chart that can give you a basic idea of how many electrons are there in each orbitals. Just copying the previous one and adding one group in front and at the back. The order of filled electrons in sublevels is related to Aufbau principle, which means the orbitals with the lowest energy are filled first. And here is the order: 1s, 2s, 2p, 3s, 4s, 3d, 4p, 5s, and so on. Furthermore, boxes can be used to represent the atomic orbitals with single head arrows to represent the spinning electrons. And here shows there are two different colors of electrons in each orbitals, and the pair of arrow shows they spin in different direction. Electrons with opposite spins tend to repel each other. When orbital of the same energy, which we call degenerate, are filled, the electron will go singly into each orbital first before they pair up to minimize repulsion. You get onto the bus, and supposedly you don't know everyone, and at the same time there's no one accompanying with you, but you don't want to stand for the whole bus journey, so you will probably to find an empty seat sitting by the window and not choosing to sit with the people that you don't know. So applying this to Hund's third rule of the order of putting the electrons into the orbitals, if more than one orbital in a sublevel is available, electrons occupy different orbitals with parallel spin, which means fulfill all the boxes with one electron first, then fulfill the spaces of the boxes. So after there's no empty seats by the window, then the next bus stop's passengers are unwillingly to sit with the people that they don't know, and at last the bus is full with passengers.
We can use the periodic table when writing the electronic configuration of an element. Let's take iodine as an example. The electronic configuration of iodine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. In order to make it simple, we can use shorthand when writing electronic configuration. First, identify the nearest noble gas to the element you want to write the electronic configuration for. But remember, the atomic number of the noble gas must be smaller than the element. So, for iodine, the nearest noble gas which has an atomic number smaller than iodine is krypton. Therefore, we can replace 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 with just simply writing Kr. However, there are some exceptions. These are the electronic configuration for exceptional transition metals. We need to know that some transition metals tend to have half-full d orbital. In order to be half-full, there needs to be 5 electrons in the d orbital. But if there are only 4 electrons in the d orbital, 1 electron will be borrowed from the full s sublevel. It is easier to understand this concept when you use the orbital diagram.